find an integrating factor, then solve the differential equation. This equation is in the form of m dx plus, let's say this is n dy equals 0. And we know that if the partial derivative of m with respect to y is equal to partial derivative of n with respect to x, if they are equal, that implies this is exact. Okay, but in this case that's not the case. Derivative of y, which is m, with respect to y is 1. So let me write in this way. Here m is y and n is 2xy minus e raised to negative 2y. Derivative of partial derivative of m with respect to y. So find the derivative of this function with respect to y. 1 n x, partial derivative of n with respect to x. So in this case we are assuming y as a constant. So derivative of 2xy, 2ny constant, derivative of x is 1. So this 2y minus, this is a function of y. So derivative with respect to x is 0 because y behaves like constant. They are not equal. So this is not exact. Now we want to find an integrating factor that will make this exact. Okay, for we check two things. We find my minus nx over n. If this is a function of x alone, function of x only, then e raised to integral of this with respect to x will be the integrating factor. If that's not the case, then we check other way around, nx minus my over m. Okay, if this is a function of y alone, then e raised to integral of this with respect to y will be the integrating factor. Okay, let's check that. Let's find my minus nx over n. So my minus nx over n is 1 minus 2y over n. N is 2xy minus e raised to negative 2y. Okay, and this is not a function of x alone. There is no way we can cancel 1 minus 2y, especially 2y and e negative 2y from top and bottom. So this is not the case, not a function. So this failed. Okay, not a function of x alone. So we discard this and go for the second. We find nx minus my over m, which is nx is 2y minus my is 1 over m is y. So 2y minus 1 over y. This is clearly a function of y alone. There are no x's. That's good. Okay, now we can simplify this further. 2y over y minus 1 over y, just separate into two fractions. 2y over y is 2 minus 1 over y. Okay, so this is a function of y alone. That's good. Then an integrating factor, let me write if, integrating factor mu, it will be a function of y is equal to e raised to integral of this with respect to y, which is 2 minus 1 over y with respect to y. Let's find this antiderivative. E raised to integral of 2 with respect to y, 2y, minus integral of 1 over y is natural log of y. Now I'm assuming y is positive. Now let's separate into 2. E raised to 2y times e raised to negative natural log of y. We are using the fact, we are assuming y is positive. Let's simplify further. E raised to 2y, that's the final, we cannot simplify any further, but this negative means -1, by the way, and -1 goes here, and we get e raised to natural log of y raised to -1. Y raised to -1 means reciprocal of y, so 1 over y. E and natural log cancel. Okay, so this is the integrating factor. This is an integrating factor for our ODE. If we multiply this differential equation by e raised to 2y times 1 over y, then this becomes an exact. Okay, let's write that. Multiply the differential equation, I generally say ODE, ordinary differential equation. Okay, differential equation by e raised to 2y times 1 over y, which is same as e raised to 2y over y. We get, so we have y, when we multiply by e 2y over y, y and this y cancel. Let me write over here. So we are multiplying throughout by e raised to 2y over y. Okay, so we need to distribute. So this one times this, y cancel, e raised to 2y dx. So we get e raised to 2y dx plus, in this case, when we multiply e 2y over y to 2xy, y and y cancel, so 2x e raised to 2y. 2x e raised to 2y minus, is a minus. When we multiply e 2y times e raised to -2y, we add the exponents. This 2y minus 2y 0, so e raised to 0 is 1, and y, so 1 over y. 1 over y dy equals 0. Okay, let's say this is new differential equation, and this should be exact because we just multiplied the given differential equation by this integrating factor. Okay, let's see. Now our new m is e2y, m is a function of xy, and new n, or we can write m xy, by the way, n xy is this. Let's check, should be exact. Here m, the partial derivative of m with respect to y, so let's find the derivative with respect to y. This is a function of y, so this will be 2e2y. Let's find the partial derivative of n with respect to x. With respect to x, 2e to the e raised to 2y behave like constant, so derivative of x is 1, so 2 e raised to 2y minus derivative of 1 over y with respect to x, so y behaves like constant 0, and they are same. Okay, that should be the case. That's why e raised to 2y over y is an integrating factor. Now we go back and follow the procedure of previous problems. Then, since this ODE, this ordinary differential equation is exact, since star is exact, let me write same, so exact by definition, there exists a function, let's say f, to be determined such that partial derivative of f with respect to x will be m, which is e raised to 2y, and partial derivative of f with respect to y is n, which is 2x e raised to 2y minus 1 over y. Let's say equation 1, equation 2, and we know the solution will be this function equals a constant, so we need to recover this function. We know the derivative of with respect to x is e2y, so we can integrate both sides with respect to x, or we can integrate second with respect to y, but number one is easier, so integrate 1 with respect to x, because this is partial derivative with respect to x. We get, so fx with respect to x, e2y with respect to x. So this is just the derivative of with respect to x, so this will be just f function. Now we are finding the derivative with respect to x, so e2y function of y behaves like a constant, so e2y there, this is times 1 dx, and entire derivative of 1 is just x, so times x, so I'm write x here, plus constant of integration. But in this case y can be a function of y, can be also a constant, so we need to write hy, some function of y. This could be a constant, just a pure constant like a number, or this could be a function of y, because function of y is also a constant in this case. So equation 3. So we just found the function f, but this is given in terms of h, so we need to determine h, and we know here is the solution. The solution is given by the function equals c. This function equals a constant is the solution, but we need to determine h. For that we make use of 2. In equation 2 we have f y, partial derivative of f with respect to y. So let's find the partial derivative of f with respect to y and compare with 2. So f y, partial with respect to y, so x is constant, e raised to 2y, derivative of e raised to 2y is 2 e2y, plus this is a pure function of y, so the partial derivative is same as regular derivative, 4. Now we compare 2 and 4 to determine h. Okay, if we compare 2 and 4, the left hand sides are same, so 2x e2y, 2x e2y, they are also equal, so h prime y should be equal to negative y over y. So compare 2 and 4 to get h prime y equals, okay, h prime y equals negative 1 over y. Okay, this is y. Now we can integrate both sides with respect to y. Integrate both sides with respect to y. So h prime y dy equals negative 1 over y dy. This will be just h y minus outside, entire derivative of 1 over y is natural log of y. We already assumed y is positive, so no need to put absolute value, plus c, but that's not needed, that will be absorbed. Even if you write plus c, that will be absorbed when we write down the final solution. So hy is negative natural log of y. Thus the solution of the original ODE or the modified ODE, modified differential equation, is f equals c. Okay, so the function is here in number 3, so that is x e raised to 2y plus hy. We just found hy to be negative natural log of y equals a constant. Final. This is the general solution, by the way.